Team, welcome to our fourth contest problem solving session. And today, instead of covering all the problems, what we are going to do is we are going to cover the problems that were solved by people in the contest or after. I guess fourth and fifth problems, they were not solved in the contest, right? Is there anyone who solved them after? Fourth and fifth problems, fourth or fifth problems. Okay, like since this is the case right now, there is no point in going over their analysis. We want to give you the room so that you can think about them in your free time, and you may be able to come up with solutions for those. So we are not going to ruin those problems for you, and we will be focusing on the first three problems. And for those problems, I think we have one person for each, right? And then they will come and present first the problem and then their solution, and they will also do the analysis as well. And then we are going to have a short discussion session in which, if people approach it in a different way, we will also consider those different ideas. And you can think of this as a very good opportunity to get some public speaking experience, as well as trying to explain your solution to other people. This is something that we do in the interviews, right? And part of it, that's exactly what we do. So this is a very good opportunity for you to do it in front of the classroom. It's even harder psychological environment in comparison to an interview, because you're just against one person, right, in the interview, or you are with one person, not against. But if you get good experience in this setup, hopefully this is going to help you. And lastly, as you guys know, these sessions are recorded. What does that mean? Once these recordings are uploaded to YouTube, you can go ahead and check your performance. Because we may have some ideas, we may have some assumptions about how we do perform, but the reality may or may not be like that. So it's nice to take a look, right? And it will give us some pointers. Maybe you're going to realize, oh, it would be better if I just speak a little louder. Oh, I'm using too many fillers. Oh, my voice is not enthusiastic enough. You may be able to get some lessons from your own performance. So that's why in the long run I highly recommend trying to come up to whiteboard. Don't frame this as, oh, what am I going to do then? It's a stressful situation. No, it's a situation that if you get familiar with, in the long run, this is going to be super helpful for you. Thank you very much, everyone. Let's get started. And who's coming for the first problem? Stage is yours.
The first equation states that we have operation to do on a list or a heap. The first one is add an element. The second one is delete an element, some elements v, and the third one is printing it. So the option I take in is using a heap to store, because if I use heap, I will get the minimum element with all five operation. But the problem with that implementation is when we try to delete an element with some value, it will lead to a time limit exit. So I use some trick. So rather than deleting an element directly from the list, I add the deleted element on a set, but it remain on the heap. So when we try to print the elements, the minimum element, if the top element or the minimum element at in our heap is found in our set, that means if it doesn't found, then we can print it. Else we can't copy elements from the element until the top element not found in the set. So then print. So if I go through the example of we have our queries in our sheet is initialized as empty. So we add 1 to our heap. So the first element in our heap will be 1, and we add 4. And we add 9. So the second element in our heap will be 9. Then we print. When we print, since the 4 is not found in our set, it will print 4. Then we delete 4 from our heap. So for that, we don't delete the element directly from the heap. We put 4 here. So the next time we try to print. So when we try to print, first we check the top element occurrence in the set. So if it's found, we put the element from this in the printer. The time complexity would be like if you have any queries, it would be the of queries that you have to do. Like, but if you have this would take us it will take I think it will take a logo paint time because the only time we iterate through the heap would be this one, and there is a query, so query style, like roof in.
Or anytime. Are we sure? When are we adding elements to the heap?
We are adding elements to the heap.
There is heap push, right, somewhere?
There.
Yes.
If
And
the query
under what, so if the query is addition, then we call heap push, right? And let's say in the most extreme case,
all the elements
are pushed.
so it will be the query time.
Query
If
time
all-
what?
If all our queries are
Addition.
log thing to push an element to it, it will take log thing time, so in the log.
And login, right? Yes. Now it is more accurate. Cool. And team, like SBC, this is exactly what we are trying to do when we are trying to come up with the worst case for the algorithm. You know, because if we forget about some cases, we may get misled. And I highly recommend doing this analysis before jumping into implementation, because many others during the contest probably did go ahead and do the heap implementation, right? Like also calling the remove function without simulating the delete operation, doing physical delete on the heap structure itself. And once we do it that way, we have seen that we get TLE, right? Time limit exceeded. And the reason was because that operation is costly. Like, what is the cost of the delete operation you use in the contest? Like the default remove implementation you use in your favorite language. What is the cost? What's that? OFN, right? And if you do it manually, probably you also did it with linear search, right? It's ON time. So now let's think of an input where delete is gonna be costly. In order for delete to be costly, we should have some elements in the heap, right? If our heap is very small, then delete operation is not gonna be very costly. So you can imagine a scenario where, let's say we put half of our elements, like half of the operations as addition, and the other half as deletions. So in this scenario, how many times we are going to call the delete operation? Like, we are considering the most extreme case. There are 100,000 queries, and we say let half of it be addition and the other half be deletion. How many times we are going to make the calls for deletion? N over 2. Right? It's 50,000 times, let's say. Okay. And at each of these calls, let's say first we do, in the first 50% of the queries, we do addition. So our heap size reached to 50,000. So if we are doing deletion in the remaining 50,000, then it means on average our queue size is, our heap size is going to be 25,000, right? Because like it will be 50,000 once we start deletion, and once we finish, it will be 0. So on average, we are going to have 25,000 elements in our queue. So as a result, the time complexity that we hit to, it is 25,000 times 50,000. And once you think about it, it's a big number. And you can change that ratio. Instead of doing it 50-50, try 3/4 addition, 1/4 deletion. Again, you're going to see big numbers multiplied with each other. So the level we want to get to is realizing this before you jump into implementation, that this solution is not going to work. Because many of us right now, we experience this with the hard way, right? We implemented it that way and then we submit. And then it said TLE. Then we get back to our approach. And in the meantime, you go ahead with the implementation. So this time maybe it didn't make you lose much. But on a different day, it could have been the wrong way that you have to backtrack and try another way. So that's why we want to minimize the time that we are using on solutions that are not going to take us to the right, or approaches that are not going to take us to the destination we want to go to. So that's why let's try to have this thinking before we jump into implementation. Does that make sense? Like this is something that we have, that we struggle implementing. You know, because of the urge of jumping into code, like let's say I'm very experienced programmer in comparison to you guys, and still it happens to me. And sometimes I find myself in that situation, without getting everything confirmed on the paper or in my mind, I jump into implementation. Like even after you get a lot more experience, still you make mistake in that end. You know, not on the other end. I almost never find myself saying, oh, why did I think about this too much? No, like we don't make mistake on that end usually. We do the mistake on the other end. We jump into implementation, we rush things a bit too much. Not like, oh, we spent so much time thinking about this. No, a little bit more verification, maybe it's gonna add 1 or 2 minutes to your total problem solving time. But the time that it can save up, it can be 10 minutes, 15 minutes. And this can be the difference between failure or success in an interview setting. So that's why the earlier we start practicing this, oh, let's get the confirmation about our algorithm first. Let's get convinced about that. Like at that time you can ask, okay, how am I gonna make things tricky for this algorithm? Like dividing the input to additions and deletions, right? That's what we did. So you can ask yourself, okay, how am I gonna put this algorithm into trouble? Imagine that's the algorithm that is suggested by the person that you hate the most. You know, he came up with the algorithm and you are asked, hey, now we are evaluating this, what do you think? Is this a good algorithm? So you should be looking at it that way. If we do that, then we will be able to see its problems. Or we are going to try some good test cases. Hopefully, it's going to either increase our confidence in the solution or help us to go for another solution if it's not working. Cool. Thank you very much. Any other questions about this problem? Any other approaches? Yes.
And I think you mentioned this to me, sorry if I'm going to repeat this again, but you said to delete, it would be 50,000 times 25,000 times log 25,000, right? Or are you, because you're starting to rebalance the heap. Are you discarding it because it's a small number, or am I mistaken somewhere?
So if you are, when you delete from the heap, you should also heapify. So that's why there is also log n component,
Okay.
you say, right?
Small. What is this?
Yes, you're right, Yes. It's even higher than that, like there is
Even
also the
higher,
log n multiplier there. You're right, thank you. Yes.
Isn't heapify an ON operation?
Heapify is an ON operation, depending on your language's choice. Like if you do the remove manually, like you go find it and then you remove, then what you have to do is you need to up heap, right? Like or actually down heap. So the last element should replace you, and then the log n down heap should happen. So you shouldn't call heapify because heapify is going to cost you ON, but you can do it manually and bring it down to log n. And I think the default implementations in your favorite language, if it is supporting that part should be done in log n. But finding the element part, if it doesn't have an index, it's going to take linear search.
So it still be ON, the process of removing, not n log n. Because we remove, then we heapify.
Oh, you're saying that it's n plus log n. Yes. Actually, Biruk is making a good point. Yes. Because like for each delete operation, yes, you make the call, but the reason the delete operation is costly is the linear search to find the element. Like we are not making log n for all the elements that are searched. After we find it, we do the log n operation to fix things up. So there is plus in between, not multiplication.
But What do I need to keep popping things from the top of the, so I might be again not getting this, but until I find the right element, so that would be M log n. Each time I pop something. Now you're doing linear search in the way the heap is implemented, I guess. Is that how you're doing? Like, if you implement the heap within C++, I'm not doing my own heap implementation. If I do, maybe I can do a linear search and delete it. Right. Then it's n, I guess.
Yes.
But in C++, I don't have access to that linear. Maybe I can, I don't know.
Well, how do you do the remove operation? Like, don't you have the linear search to find where the element is located in your heap?
I do, I just keep popping things up.
Okay, so then yours is M log n. You don't have to do it that way.
Yeah, I can just keep it.
Okay. Cool. Any other questions about this problem? Alright, in that case, let's continue with the second one.
So the question states that there are two friends and they're buying ice cream flavors. The question states that neither of them will buy what the other has purchased, and we're given a set of prices for each flavor. So this is the area of the ice cream flavors, and they have a limited budget. I think it's 6 in this case. So the question states that wherever they buy, each price should add up to the total budget they have. So in this case it would be, and it also states that the solution is always unique. So in this case it would be 1 in 5 actually. So this would 1 in 5. If one purchases this an ice cream flavor with this price, the other would purchase an ice cream flavor with this price. So this would add up to 6. And off the top of my head, I came up with a naive algorithm which would take all of n squared and the implementation. I use the for. Should I write the code? Okay, so I use the for loop to iterate to go through the array to find the first price, and I checked if there is a counter price in the remaining array. If I find the first price, and if the other, for example, if it's 1 and if 5 is in the remaining array, then I would return the indices of the first indices and the 5 indices. That's the solution. And time complexity, I'm not using another additional species, so the space complexity would be of 1, and the 1 would be of n squared.
Okay, so that's the naive solution, right? And then how did you improve on that?
I actually did not. I proceeded to the next questions.
During the contest.
Yeah, during the contest.
Okay. And right now, the solution we see on the whiteboard is not this one, though, right?
What is this one?
It is this one.
Yeah. So I iterate to the array, and if there is an adjacent additive for the current element, then I return the indices. And since it's not zero-based indices, so I added 1 and I added 2 here.
So, what does this index function do?
It returns the index of that element
If it exists,
if it exists.
and it is the time complexity is O(n), right?
This one will take on and
Yes.
checking its in Python, so this function takes on n.
Oh, the if condition also takes
Takes
O(n).
an
And then how about index part? Is it also taking O(n)? That's also taking O(n), right?
No, it's a list, so I think it knows where the indices are. So I
It's a
think
list.
that would be of 1.
But you are looking for the value, right?
Yeah, this part, I'm looking for the value, so this one will take O of n. the first part, the for loop will take all of 1, and then this part will take all of, no, this one will take all of n, this one will take all of 1.
So that part I'm not so sure, is it? Because it's list, right?
Yep.
It's list and you are looking for a value. So basically it's trying to find the first index of m minus Ri, right?
Yeah.
So probably it should do a linear search for that. Meaning it's going to be O n time. That part. And your overall time complexity does not change because of this, but that's also O n. So I'm just pointing this out because especially when we are using a language like Python, some function calls can have hidden complexity. Let's say now you said that this is O(n) squared because the in part on the if condition, it was O(n), right? That's why you were able to see that it was n squared. But let's say that if condition was O1, but because of this index call, again your algorithm would be O(n) squared, right? Does it make sense?
Yeah, it makes sense.
Okay, so since the total time complexity can be O(n) squared because of such function calls, or let's say such function calls sometimes can be not in constant time. It can be like log n. It can be linear time O(n). We should be careful with their time complexities. So in our favorite language, let's get to know about these functions. Like if you are not sure, read about it. Just ask to Google. Then you'll get the answer. So this way, hopefully, in the long run, we should accumulate this language knowledge. Because we should know our favorite language well to perform well in the interview. Cool. Thank you very much. All right. Any other approaches for this problem? You have one? Yes.
I think it does it in all of n time and all of n space. So it would have some issues with space, but it would see this significant amount.
Can you speak a little louder, please?
Oh, it's the matter of this. So it does it with all of n space and all of n time. What I did is I finished everything in one pass. So I would go over the list of numbers, and then when I go through the list of numbers, the first thing I do is I store the number I found in a map, and then I'll give it a value, an empty list first. And then when I find not an empty list, a list with the index of the number, its position. So if I found number 3, actually we could use. Can you show me the input? Okay, so if I'm not wrong, so I get 2, 4, 5. I can't remember this, but these were. These are the inputs 1, 4, 5, 3, and 2, and we are expected to find, I think, a combination of 6, right? So what we do is we go over this list, and then when we find 1 in the first position in the map, in the list, we store it in a map, and in the map we store the index of 1, and we give it a 0. And then when we find 4, we do the same. So for every pass after storing the number, we also check if target minus num exists in our map. So if this value exists in our map, that kind of means either we've passed we've stored its counterpart in our existing map. So that would mean if we don't have a duplicate, when we go to 5, we would see that 6 minus 5 would be 1, and we already have an index of 0. One more thing we would have to worry about here is, let's say if we have another 3, and if we come here, our edge case would be when we have a 3, and then if we see another 3, we have to make sure that the number is not the same index. So in that case, we check if the length of the value in the value stored as a key, the value stored under the key of our current index is different, is more than has a length bigger than 1, and if it's bigger than 1, and then that's it. So we return the index of these 2. Otherwise, we just return the index from the dictionary. Is it clear, or did I still get much? Did you get my solution?
So
Anybody?
can you clarify the last part? Like you basically do two things. You either look at the dictionary, or if they are equal, you do something, right?
Yeah, so if they're equal,
Yes.
actually, this is when I think of it, this is unnecessary. I was making sure I didn't pass over the same number, but because there is no possibility of me passing over the same number twice, this part is more or less unnecessary. But if there was a duplicate in the list, but they said this input said we can't have duplicates. It said all numbers are going to be unique, right? So it's unnecessary.
I guess not. The second example has two tools, right?
Oh, in that case then, yeah, but we can select duplicates. Okay, they cannot have the same ice creams, if you remember. So they said the two friends, they're not going to have
different numbers.
Yeah, they should have different numbers. So we should check if those two numbers are different. So I think that's.
But like since they are different flavors, are they not able to get those two? Let's say for the second one, the answer is 1, 2, right? And they both have the same value. It's just like they don't have. They should choose two different flavors, but the flavors can have the same price.
Oh, I see. So that part is kind of unnecessary. So I don't have to check whether or not I'm passing over a duplicate, because I would only be passing over a number once. So I would only be storing it here if there's a different value. So if the length is more than 1, I would just return the index is stored in here.
Mm-hmm. So like equal values basically wouldn't cause any trouble for you.
Yeah, exactly. So that
Because
was
once you see the second appearance, you are gonna see that the first one was in the map.
already done. Yeah.
I see, makes sense.
So,
And maybe can you quickly walk us over your code? Like
okay,
this
I need
discussion
to-
was a little bit too high level, I guess,
I
right?
Should I upload it? Like I didn't push the code to GitHub, but I think it's online. So this is the unnecessary if statement, but everything is the same. So I'll go over the numbers. I have the num map initialized as an empty dictionary, and then when I find a number, like for every number, if it's not in the numbers map, I would create an empty list, and then. But if it already exists, I'll append it to the existing list in the dictionary, and then so I'm taking this is just a count. So the number would be from the nums. It would be the nums, the num I. So I'll take the number and then I'll subtract it from the target. The target being this number passed from the ice cream parlor function. I'm using the exact TwoSum function by the way. So and then what I do is I check if it's in the num map, and that would be, since it's a dictionary, it would be a constant time lookup, and then I check target is different from num. If the target minus num is different from num, I check this to see if those are duplicates, but this is the unnecessary part that I was working out here, so this could have been removed. But so when you come here, if target num and the length of nums is greater than 1, this means that it's already found, so I would return the index. Since we're using a 1-based index, I would return the index plus the indices plus 1, and yeah, that's what we'll say.
Thank you very much. And as we see, there can be alternative solutions, and some of them can be more efficient than the others. So usually, in order to get better time complexity, you might have to use a little more memory. If you can find some data that will be useful for you, you can calculate it, reprocess it, and then it can help you to decrease your overall time complexity. Thank you very much. And let's continue with the third problem.
Lauren has a list of prices for a house over several years, and she buys one house and tries to sell it on another year, and she's trying to sell the house with minimum loss. And, my solution is I use the HIP and a hash map. I use the hash map to store the index. For example, 420, 0, 7, 1, 8, 1. And first I'm going to pop from the HIP, I'm going to give 20. Then I'm going to pop again and I'm going to 8. I'm going to give 8. Then I'm going to subtract 20 from 8. but I can't subtract 20 from 8 because 20 comes before 8.
How did you get from 20 to 8? Like, did you...
Huh?
What's that? So we inserted
The
them all in the heap?
maximum, I used the maximum.
Maxi. Okay, okay. Okay, so did you insert everything at the beginning to the heap?
Yeah.
Okay.
So I'm gonna subtract 20 from 8 and the mean value is gonna be 12. And I'm gonna store 8 and a 10 value. Then 8. Then I'm gonna subtract 8 to the next max value, which is 7. But I can't subtract this because 7 comes before 8, and so this is not possible. So I'm gonna store 7 in P. Then I'm gonna pop another value, which is gonna be 5. So 7 minus 5. Then mean is gonna be 2. Then I'm gonna pop again, and which the last value was 5. So 5 minus. Okay, I think I'm finished. So the answer is going to be 2. The time complexity is going to be n log n since I inserted every element to the heap, and inserting to the heap is going to cost me n log n. So it's going to be n log n. And the specific complexity is going to be O of n since I did the heap in hash map.
Alternatively, you can call heapify on the array, like after adding all the elements into your list and then calling heapify on it. Since heapify operation is on, you can do that part, initial heap creation part in on time. Does that make sense? Like if your favorite programming language has heapify function in it that works on the list, that function works in on time. Is that heapify function? What's that?
I need the index.
You need the indices as well, so you can go over the array for the first time, and then save all the indices into a map, and then call heapify on it, then it's going to be on time. But still, like moving forward, you are removing elements from the heap, so you are going to get n log n time complexity anyways. I was just saying this because like it would be nice to know that heapify works in on time. So if all the elements that are going to go into the heap are known from the beginning, you can make use of the heapify function. But if additions and deletions are happening, interchangeably, then obviously you're going to go ahead and use the regular functions.
Yeah, I'm using remove source.
Yes, yes. Cool. Thank you very much. So now that's a good solution. And now let's focus on how to explain the solution part as well. Because this is also something that we want to get better at, right? In the interview, that's what we are supposed to do. Maybe not like this, because we are not supposed to do everything and then explain everything. In the interview, it's more like back and forth, right? We do some and then we explain some. But still, when we are prompted to explain solutions, I think it's better to focus on what parts we can improve on. So here, like your solution is working pretty well and you have very good ideas in your mind, but not everything you have in your mind is in the audience's mind. Meaning, when you start the execution here, you first get 20 and then 8. It wasn't super obvious whether everything was in the heap, right? So at that time, if you were going a little slower and first saying, okay, so what we do is we insert all these elements into a heap. So first we have 20 here, and this is going to be a max heap. And then we get 7 inserted, and then we get 8 inserted, and then we get 2 and 5. Indeed, we got lucky, right? We didn't have to make any kind of switch. But once this is here, then you say, okay, so now we are going to get 20 from our heap. So this is deleted. 5 came up here, and then it's left with this. So, oh, this is going to be actually 8, this is going to be 7, this is going to be 5. Yes, and then you get one more, so you get 8 this time. And now you look at the difference. And when you are looking at the difference, actually, the difference is not the only thing you care about, right? The second thing you care is whether 20 and 8, they are eligible. Meaning, if 20 is not coming before 8, right? We cannot use this value. consider this value whether it is better than our global result or not. So for that reason, we should also do the eligibility check. So we look at the indices of the index of the 20, which is 0. And we look at the index of 8, which is 2. Since 20 is coming before than 8, this is a feasible solution. So I get 12 as my minimum. And then I continue. So next time I do pop after 8 from heap, I'm gonna get 7, right? So this guy is gonna go, 2 is gonna come up here, it's gonna be replaced with 7. So once 8 is removed from the heap, it's gonna look like this. And then once we also remove 7 from this, it's gonna look like this. And then I'm gonna be considering 8 and 7. And when we look at their indices, 8 is at 2, 7 is at 1. So can I consider this as a candidate? No, because the 8 does not appear before 7. Therefore, this is not an eligible solution. I don't even consider whether this is better than my global solution or best solution I found so far or not. And we continue, and then we get 5. So this time we do the check for 7 and 5. And when we do the check for 7 and 5, we look at their indices. 7 is at 1 and 5 is at 4. So 7 comes before than 5. Therefore, this is an eligible solution. And then we check whether 2 is better than my best found solution so far. Yes. Therefore, I make it 2. And finally, we get 2. And we have 5 and 2. So let's check the eligibility. 5 is at 4. 2 is at 3. They are not eligible. So we don't consider this one. So, yes, this is a good working solution. At the same time, did we prove that this is a working solution? Now let's think about that. So, when a solution is eligible, there is no problem, right? We compare it against the best solution. So, we don't cause, or there is no risk of causing any trouble. How about a solution is not, when we face with 2 numbers that are not eligible? So, let's consider the case of 8 and 7. Okay, 8 was not eligible with 7, but maybe 8 was eligible with 5, right? Why did we not consider that as a candidate? Can somebody tell me? So with this solution, we consider 8, 7 and said this is ineligible, right? And then we switch to 7, 5. There was also a feasible solution for 8, which was 8, 5, right? But we didn't consider this. Why did we not consider this?
8 subtracted 5 is 3, and 7 minus 1 is 2, so we should consider
7 would be a better solution, right? Yes, so very good point. And it's very nice, like it would be very nice to underline this. Basically here, once 8 is not eligible to 7, moving forward, there is no point in thinking whether I can get a better solution with 8 or not. The reason is 7 will always give me a better solution. Why? Let's think about that. So, the reason 8 is not eligible to 7 is 7 appears before than 8, right? This means in my input it is something like this. There is 7, there is 8, right? So the input is like this. For something to be eligible with 8, it has to appear after 8, right? And then it has to be smaller than 8. So we are looking for something in this area that is smaller than 8. So if it is smaller than 8 and in this area, and I know that there is nothing between 8 and 7 because they came out one after another from the heap, right? So if there was something, then it would have come in between. So I know that they are consecutive to each other. So, if this number is smaller than 8 and eligible with 8, would it be ever possible that it's not eligible with 7? No. It will definitely be eligible for 7 too. And if it is also eligible for 7, would it ever make sense to consider the solution with 8? No, 7 is better because we are trying to minimize the difference. And we know that 7's difference is going to be always smaller than 8's difference. So that's why we don't have to consider that. That's why we are able to keep proceeding, right? And considering only the last 2 elements. Cool. So when you are explaining your solution, if you try to cover these points, it would be better. Like try to imagine you are explaining this solution to somebody that doesn't know the question or answer, but that speak the language. Meaning, if you tell them anything about programming, they will understand. Let's try to explain our answers this way. I think it's going to be more helpful for us. And at the beginning, it's very normal that we are not doing it this way. Guys, we didn't get much of an experience of this. So how many times have you tried to do this in the past? Is there any person who tried this more than 5 times? Can we see hands? Including group 1 members. Maybe it's more than 5 times for you guys. So you should raise your hand. Yes. And when you see these people in the whiteboard, you are going to see that they are now feeling better, like they express their ideas in a better way. So if we compare today's Biruk with 1 year before's Biruk, which one would explain ideas better, Biruk? Right? And the reason is because the practice is helping. And the same is going to apply to you guys. As you do more practice, you're going to get better at this. So thank you very much for everybody who showed the courage to come here and explain their solutions, share their solutions with us. It was a very nice session, and we will continue on Monday. So please enjoy the rest of your weekend.